Yeah, that should be going. Hopefully I'm sharing the right screen. So anyway, so welcome everyone to this build your own operating system class. My name is Anton Forza. I'm associate professor here at the School of Computing. And I'm a little scared that I see some unfamiliar faces. But anyway, so let's quickly talk about what this class is about. So it's a typically graduate level, but undergraduates are welcome. Like I expected 20 people, but we probably have a little bit more, but everyone is welcome. The reason I mentioned unfamiliar faces and I'm scared about those is that I kind of expect that we need the only prerequisite for this class, and I assume everything else is like easy, but the prereq is to have a ideally x86 based TF50, 5460 class from me, right? Or from someone else, but equivalent class, meaning that you kind of already looked at the operating systems in details. It's not some kind of a fluffy high level class, but really can like know assembly, can debug low level code, stuff like that, right? So without it, this class is hard. If you've done it before with me or someone else, then you should be fine. And we can talk about it. So if you like, I'm very flexible, especially in this class. So the goal is to help everyone to learn as much as possible. So talk to me if you don't have this prereq, right? But anyway, so myself, right? So you have a web page, class web page. So that's not that important. Like some background about me. So I historically built operating systems since I was younger than you. When I was in my undergrad, I decided I gonna specialize in operating systems. I think it was around 1999, and since then I'm building one after another. Not everything is an operating system, but some of those are like clean slate designs, like this E1 OS is like a childish distributed operating system project, which I was building as a student, and I built like this micro Itron specification. It's like embedded specification, popular in Asia, like a industry standard. And I ported it or like implemented it on top of it. L4 microkernel. Again, if you don't know it, L4, it's one of the most prominent microkernels. So while we use microkernels today, and as a PhD, I built this deterministic replay engine. So essentially, the idea was that you take a virtual machine and then you record its execution, and then you can replay it later, right? And Zen is a production quality virtual machine, which was used by Amazon and possibly still used in Amazon Cloud, but they are kind of like deprecating it, moving to something else. Then I built a range of like heavy lifting extensions to Linux, but the most recent ones, Redleaf and Atmosphere, are the two operating systems implemented in Rust. So let me just, if I can get to that screen, I'll try to move this. Not sure if I can, though. My own wonderful face. Not sure, but how do we do this? Any ideas for how to move it?
Get a full screen.
Get a full screen. The escape. And then I can move. Yeah, thank you. Jesus, you guys that's clever. And now I have to go back to full screen. Yeah. So these are the most interesting ones which we build with my students. Redleaf is a clean slate operating system in Rust, which uses Rust safety of the Rust language as an isolation mechanism. And it was kind of very new as of like 5 years ago. I think we published in 2020. Now it's less interesting, and I will explain why. But still, it's a good, interesting design. And this most recent Atmosphere, which we just recently we are publishing still, which was just accepted this year, It's a fully formally verified microkernel in Rust. So it's essentially Rust and formal verification. So you have a mathematical proof of why it's correct. And we're gonna talk a little bit more about it. But essentially, okay, like, if you took a class from me, this is what I do on a daily basis. So I build operating systems. I care about it a lot. So it's fun to teach, obviously. It's not that I like very good at teaching, but at least, you know, if you ask me a question, I will try to answer. The idea of this course, and I will come back later to this and talk about the whole, like, kind of like, I teach 3 classes and how they fit together, but this one is specifically build your own operating system, right? So I kind of argue that let's do it in Rust, but if there is significant pushback, we can do it in C or something like that. Or most people can do it in Rust, or half people can do it in Rust, and half people can do it in C. But I still argue, let's try in Rust, because, and worst comes to worst, we'll figure it out, right? And I will argue why later today, but for now, like, it's clear with me for a sec. But if you want a more concrete overview of what will happen, and we'll talk about what it means to build a new operating system. And we probably, if you took this CS5460, what is it, 5460, then you kind of know what it is, right? But like the plan for this year is that each of you build your own version of a tiny kernel, which first boots into Rust, meaning that you initialize execution environment in x86 with segmentation and paging, print hello world, have like a serial line driver or something. We create a first address space, meaning that we manipulate page tables. That's kind of similar to the homework assignments in the CS460. Then okay, we have an address space, which means we have a abstraction of a process, but it's empty, right? So you're gonna load an L file, which you compile. It can be also Rust or can be C, it doesn't matter. So most likely we'll try Rust as well. And that essentially means that, and you build the first system call, and then you get like hello from user at this point, right? So you can run user run. Then we implement a timer, and like really we just need timer on the keyboard or serial line, whatever it is, to make sure that we can context switch or initiate the context switch between processes, right? We build context switch and we load 2 processes. One of them can be shell or maybe still be hello world. We'll see whether it's shell or not, but we have a context switch then. And then there's a two processes and they need to communicate with each other, and I explain why and everything. So we have to build this inter-process communicating mechanism. So essentially in x86 it was just pipe, right? But we will build something a little smarter. And hopefully if we get to that within the course of this semester, we can build at least one user level device driver, right? So yeah, at a high level, we're going to build a microkernel. Just everything is user land. I will come back to it, but just as an overview, right? Okay, cool. So that's the idea. So obviously, everyone like more concrete. What will happen is that I'll try to teach on first high level idea of what is it we're building next. So like if we're booting into Rust, initializing x86 execution environment, we're going to talk about what it means at a high level. Then most likely, I mean, I never taught this class, so I'm trying to like figure out how to do it in the best possible way. I would say let's read through some source code of existing system which does it, right? And then you look at the source code and say, look, yeah, I understand what's going on here, and then I can build my own implementation, right? And you build it as a homework, right? And roughly we'll have 5 or 6 to get to the user level device driver, right? And as we go forward, like we will talk about different tools like QEMU, because it's hard to build on real hardware. Like in production, you build on the simulated environment. You've seen QEMU in x86 class, right? So it's not a big surprise, but we kind of like spend a little bit more time on what kind of tricks you can do. Because in this undergrad 5460 version, like, people are a little lost with QEMU. But I mean, I think we're getting better. We switched to Visual Studio based setup because it's like less, I guess it's less offensive to people. So like they tend to use a little bit more, but it doesn't really matter. So we'll get there. So, and as we go forward, and like we're going to discuss what is it like, why are we building a microkernel? what kind of IPC flavor we need. And we will read a couple of papers to kind of get us to this, to understanding, like, will allow us to understand what's going on in this microkernel space. And at a high level, we're going to build something, a CL4-like. I mentioned this L4 microkernel. CL4 is the modern verified version of L4. Again, kind of the standard canonical microkernel design with lots of interesting nuances, but we'll take a look at what is like what are the most important parts of this design. And then again, if you ever get a job which says, okay, build me a microkernel within the course of like 3 weeks or 3 months or something, you will, it's a very solid foundation. So you can take it, run it in production. So this design, it's not a joke. So people build systems like that. Like Google builds whatever, something similar, whatever they call it. Fuchsia or Magenta, what is it? Their new microkernel. Okay, so then grading. So it's a good class, no finals, no exams, nothing, right? Just the homeworks, right? And in-class participation, just to make sure that people still show up. It's fun to discuss. It's not fun to teach to an empty room. I understand that you cannot always show up, but that's essentially the idea. So, right, so just building. I don't have a TA at the moment, so there might be a half TA, but might not, we'll see. So I don't know how to grade those submissions, or like, it's hard to grade given like 25, 30 submissions. Most likely we'll have autograder set up, which will help you to submit your code. But to some degree, I just trust that you submitted something meaningful and pass those tests. So again, the class is not about, not about grades or anything, just about learning how to do it and me helping you to do it. Like a couple of notes, all the work has to be yours. Feel free to discuss the code, show the code to your friends, do whatever. Like if help your friend to debug it, it's fine. Just final submission has to be yours, right? And as for AI use policy, I mean, let's use AI as if we were in production, meaning that if you don't know how to write a for loop in Rust, go for it, let AI write it for you. But just, I would say, don't single shot the assignments. It may be possible, it may not be possible, and maybe by the end of this year, AI will become even more powerful. It's already very powerful, right? So, but again, if you just blindly submit something AI generated, you're not learning anything, and I don't have resources to police you that much. So just do it as if you were like. It's not that I do a lot of coding, but if I do some funky, whatever, some Python nonsensical stuff, I do ChatGPT, and it writes me whatever the for loops I need to access, whatever I need to access, right? Okay, so any questions about this the logistics?
Will the project mostly just be like one SQL?
You can take it. I was thinking about x86 just to simplify for everyone. I don't think we need to I don't think you will learn that much from switching between architecture sets. So I would say, I know x86. That's whatever, the best I wanted to say, but not the best, but at least I spent the most amount of time on x86. And then what I observe in practice from my students, they quickly switch between instruction sets. There are some quirks in how CPU implements isolation on ARM and RISC-V, but you usually can switch without much trouble.
Are these group projects?
I would say let's do the video for now. I don't understand, those are not really projects. They're more like homework assignments. And the whole idea of this class is that you build and you learn from building. And arguably, well, in my second part, I'll try to get to the point, why would one do this, right? This class, it's hard to, I mean, everyone will have their own opinion, right? I cannot say that I know the answer. At a high level, if you learn, you probably can make a career out of it, or some version of a career. We'll see. So let's say individual homeworks, but feel free to discuss. So again, limited resources, limited PAs. So if you ask your friends, okay, guys, I don't understand what's going on, show me how you build this page table, that's totally fine. Just then rewrite your code. And by writing is like it's a different form of thinking. Better understand what's going on. If you especially debug this stuff, and you 100% know what's going on. And it will help you later, years from now, to debug something else. But yeah, any other questions? All good? Okay, then let's switch this one to kind of like, I forgot to ask you guys. So what is our standing on Rust? So who is comfortable with Rust? So 4 people. That makes my job a little harder. So, I mean, we can do it in C, and that will be fine too. But what's the vote? Do we want to do it in C? No, no one wants it. Yeah, that's what I was thinking as well. I mean, my Rust is also, yeah, not fun. I mean, I was coding last time. I was coding on Redleaf, right? And it wasn't like very good either. Compared to my students specifically, especially, right? But so I will need your refresher, but yeah, sure, then let's go with Rust. I totally agree with you. Okay, let's quickly switch to the next, to the intro lecture. Okay, let me double check that I'm sharing this one. Oh, yeah, cool. Okay, so kind of, okay, so then most likely we'll have to spend at least some amount of time, at least to look at Rust, but I also will trust you to, I will probably just assign bits of Rust book. There is the like official canonical Rust book, right? Which forces you to go through some exercises to get some basics of Rust. That's probably one of the best sources. If you have a better source, tell me. I don't know whether I want to assign it as official assignments or just as maybe something has to be official, otherwise no one will do anything, right? But essentially, yeah. So then let's stick to Rust for now. But if disaster comes, we'll see. But okay, the most important question we all have is like, why would one be interested in building a new operating system, or in specifically, why would someone like you take a class like this, right, and invest your time into it? And historically, and it's true still now, like the systems field was paying for these 2 things: performance and security. And performance is probably the major driver. I'll talk a little bit about it, because we get new hardware, it's more powerful and everything, right? So people immediately want to monetize on this hardware. Security was kind of a good driver for the last 5 years before the AI boom, right? AI kind of said, okay, forget about everything, just let's do AI. But the thing is that, I mean, security is harder because it doesn't immediately translate into any money or revenue, right? So it's harder. Maybe you will pay a fine later when all your data gets stolen, but we don't have a good legal framework in place to force companies to do anything. But anyway, if you're a researcher, you'll be worried about security. So let's talk about security first, right? So a high level observation, which I keep making in all these classes, is that if you look at this figure, those 2 guys, Ken Thompson, Dennis Ritchie, invented Unix, roughly speaking. They're coding in 1972. We don't even have screens to terminal, right? And that system which they created, which we studied as x86 in our undergraduate class, it's the system which we're still running today, right? So it got larger, it got ported and adopted to all sorts of hardware, right? But it's conceptually the same Unix architecture, written in the same C language, with all the bugs, right? And now it's also concurrent and highly parallel, so bugs are even trickier. But it's kind of not fun because we started running those systems on all sorts of like various hardware, and some of them are mission critical. And again, the reason, like, there are multiple reasons to put all these things on the slide, but a couple of reasons is that this is potential market where you really sell your own kind of new microcontrollers, because the whole market historically was running a bunch of microcontrollers, and it was too expensive for isolation. You know, if you get into one of them, you don't own the full car. And now they say, look, we're gonna put it on one generic CPU, but just provide us isolation software, ideally with some formal guarantees to make sure that, you know, if you break into it, into your infotainment system, you still don't own the entire car, right? And so that probably is still like an area in which you can sell a new operating system. Because I'm not saying that you're gonna like replace Linux or anything on a desktop or Mac on a desktop or Linux in a data center. Possible to like do parts of it, but it will be hard. But these are still like embedded systems and different funky setups is still possible. So people are still looking into building operating systems, right? And the main reason is that this Linux kernel, which we're running, like I think on the previous slide, maybe all but one system was running Linux. And Linux today, and it's from probably last year, so it quotes 27 million lines of code. x86, remember, was 10,000 lines of code, right? It's giant now, 40 major subsystems, hence 10,000 device drivers roughly. At this point, you know, written in C, like unsafe, it's very hard. If you take a look at Linux kernel source code, like if you spend enough time, originally you just say, wow, it's a lot of code. But then if your goal is to find vulnerabilities, meaning exploits, which can give you control over this system, you kind of quickly start thinking, just see that those are possible. I actually don't even know how this thing runs correctly. And then no one really knows what correctly means because no one really specified anything how Linux is supposed to run or any of those subsystems. So like loosely defined, right? You can always invoke functions of out of order. And I mean, I'm saying always, but that's one way to achieve an unexpected state in which this Linux essentially says, okay, I'm crashing or whatever, right? So at some point, and that's kind of like a distribution of vulnerabilities. And people were kind of lazy in early 2010. They were finding just maybe tens or hundreds of vulnerabilities, right? Do you guys understand what vulnerabilities are? Essentially a way to exploit the kernel and do whatever, like roughly become root. But like spikes happen, but like kind of everything was growing up to the point that at some point in the Linux kernel, the idea which was around for a while, they said, okay, look guys, instead of like designating some specific bugs and vulnerabilities, we'll treat almost every bug as a vulnerability. And they became a CE assigning authority, and they say, look guys, like we believe that, first of all, for a while, people believe that only certain bugs are exploitable, meaning that, you know, if you have a benign bug, it's not an exploit, but then exploitation became so advanced and automated that almost everything becomes exploitable. And here in 2024, they don't even have data for 2025 because it's like insolvents, right? But they said, okay, we believe that we have that many vulnerabilities. Almost every bug is a vulnerability in a Linux kernel. And that's kind of true for most other kernels. So it's not hard to exploit if you're like do it professionally. And the point which I'm trying to make is that honestly, it's not going to change. So if you find a bug in a Linux kernel today, you most likely have a way of owning the machine, or at least causing a denial of service, meaning that machine will crash or stop doing something, right? And with the technology which we have today, which is unsafe C, 27 million lines of code, minimal testing. I mean, I don't know if there are people who do fast testing. Kind of for you, it was a gold mine, you know, it's endless, you know, endless 27 million lines of code of vulnerabilities, you know, you can publish paper after paper after paper in a fuzzing domain. But really, if you think of how to fix this, there is no easy way to fix, right? Unless you start from scratch, really, really carefully. Really no real way. So people care about it. So security is still there. And I'll explain how we can try to kind of like change this. And the second kind of idea is performance. So performance comes to you in this kind of performance will stay around for a while. AI will drive performance as well. So roughly speaking, modern machine, which you take in a data center, looks like this distributed system. So this specific diagram, which you've seen from undergraduate class, is 4 sockets, like 4 physical CPUs, which you get plugged on the motherboard. They're connected with this QPI, quick fast interconnect protocol, essentially kind of forming the network and the system. Each socket has multiple cores. PC board is one component today in the server space. Each of them has private memory, and it's called a non-uniform memory, meaning because this socket can access the memory, local memory, much faster than remote memories, because it has to go through QPI links, and it has a local PCI bus, so it can also access PCI devices much, like local PCI devices faster and with lower latency. We kind of code against it, right? So if you take a peek at a Camulab data center, which is in the MEB building, right? That's a photo from 10 years ago, probably. Each blade is roughly, that's their most powerful blade game used to be, but that's the one which has 4 sockets. And so 2 on the first floor, 2 on the second floor. They're connected with the QPI for the local memories. Don't show PCI buses, but sure. And there is locality. So that's your typical data center, right? And it's been like that for a while, right? And Linux was struggling to adapt to this system because of coherence bottlenecks and stuff like that, scaling to multi-core, but actually it did quite well. But if you ask yourself a question, okay, guys, what the hardware will look like in roughly 5 to 10 years, if not today, what will be your answer? A lot more PCIe, yeah, okay. This guy works on PCIe. Any other ideas? What will change?
The GPUs that.
Yeah, GPUs. What will happen to GPUs? Yeah, the GPUs are sitting somewhere here on the PCI bus. You're right. So GPUs will be there. What else?
Accelerators for cryptography.
Correct. So a ton of different accelerators, right? And I mean, maybe you've heard it from me, maybe it's from your own experience, but you're right. So the idea will be that in the future, like arguably, majority of the workloads will not run on those general purpose CPUs like we did for the last 40 years, but will be running on various forms of accelerators, connected arguably by PCIe or some other variants of low latency buses. And that's where your GPUs are coming, but GPUs will not be the only accelerators, right? And again, there will be some memory locality, even more drastic version of non-uniform memory, where memories will be different speed, different capacities, but you have to code, and you have local and remote memories. But you will have a bunch of, probably something will be running next to the network interface, kind of like near network cores. And most likely, and it's already today, stuff is running near storage. It runs near NVMe devices. There are startups which like push your SQL queries towards like to execute like filtering or something near on the NVMe devices themselves. But we also have non-volatile memory and like different proposals for how to essentially co-design memory and execution units near memory, and that's coming, right? And the question is like, how will you design a new operating system which somehow leverages this hardware? So you can start with Linux, but most likely it's not the best way to go around. And something like a data flow graph, which maps on those execution units, kind of makes sense. That's what we were kind of teaching to our donors to give us money. And you will probably have Linux somewhere, more like you have it in the data center, which implements this control plane, which essentially like allows you to have your SSH and other tools, but really stuff is running on those tiny microphones which are loaded on those execution units. It might be different. So there might be like so bare bones that you cannot even follow the system. But again, partially to learn what the operating system is, the minimal things which you typically want as isolation, meaning that you can say that there's two different processes and they cannot access resources of each other. You need sharing, which means that you need to build context switch and essentially switch from one user to another. And you typically need communication, meaning that you would say, look, there's a policy and one user can send something to another, right? But even in this system, it gets very, very funky. So how will you, it's no longer a CPU where you can do a context switch and switch from one process to running one to another. Here, if like a more privileged process comes in and says, look, I want your near network cores, like, those disappear, and you probably have to rescale this graph of computation, kind of like you do in the data center. Say, wow, my front end disappeared, so there's no reason to run the backend. Like scale everything down. So it gets tricky. So we don't know the answers to this. So, but people are looking at those problems. And so, as I said, security and performance will drive it for many years, for as long as hardware keeps changing, right? So that's essentially the idea. And again, so if trying to motivate you guys to take this class, so my idea is that my experience and experience of my students is that this knowledge of low-level systems still pays, like, you know, and arguably will continue to pay even if AI takes over. Someone needs to build those low-level systems, and this knowledge is hard to replace, arguably. So it's not easy to explain to AI what it is that you're trying to design, right? So, and that's kind of the message here is that you will have to specialize in something. I'm not saying you have to specialize in systems, but that's one way. So if you're specializing in system, then it makes sense to take this class as part of this OS sequence, right? And the two kind of gateways, like it's again, it's performance. So my students and I, we are experts in this cycle level optimizations. Even today, we built the fastest ever hash table, and I keep talking about it. It was the fastest ever 2 years ago, and then later someone else built another one, which is faster than us. But the interesting observation is that it used to be that in this hash tables field, you know, improvement of 20% gives you a publication. Ours was twice as fast as any existing competitors, just this low-level optimizations to the extreme, and it was twice as fast as anything, which is pretty cool. And then another team comes back from QOA and they say, look, we actually built the one which is even, again, twice as fast. Now we're working on the one which, again, will be twice as fast. So it's all, you know, essentially very deep understanding of this diagram and how to extract performance, essentially. Where is the bottom? And our hash table saturates those links, memory bus. Historically, hash tables are about latency. That's how we think about them. We kind of said, okay, memory is no longer synchronous. It's asynchronous. Never type, it's always prefetch. Prefetching is hard. So, but essentially, there is a way to saturate the memory bus. QPI as well is saturated, and then very carefully I design the code to make sure that you saturate your CPU as well. And it's fun. So people will pay you money. So today, if someone like who does high frequency trading probably will pay you money. Tomorrow, AI people will pay you money. Like our not competitive, but papers which were recently read in the meeting were from the AI community. Essentially, for them, access to memory is so important. They kind of go off with the same idea. They want to access the memory in such a manner that you saturate the memory loss. And they have papers on how to prefetch stuff and make sure that those links are completely saturated. So essentially, that's hopefully where you will be, like after this class. So essentially, one level of in-depth understanding of what's going on. And so essentially, when you build your own OS, you're like one level down again. It's not just theoretical. You understand the low-level things involved. You're not going to be immediately an expert in performance, but it's one step closer. We will talk about it. We'll talk about how to debug performance, how to make things fast. But essentially, unless you understand, like the goal here is to understand your execution environment top to bottom. From good on the hardware, you set up execution environment like page tables and stuff. How many levels you set up matters because that will control the amount of TLB misses you will have, right? So all these things you have to know. The moment you know, you can do this optimization, you get paid for it. And for security, so people who do a security research, this class essentially will allow you to go in one level down and talk about like how people exploit the very the foundational software, which is a operating system, hypervisors, stuff which runs under the hypervisors, like essentially BIOS, and those things like bits of firmware, like Intel management engine. I'm not saying that we're going to talk about them, but when you write your own system and you say, look, I'm dereferencing a pointer here. Is it safe? Does it point to anything? What makes sense? What is still alive? Or even the same type? If you build those things, then you can move forward and like answer similar questions about other systems like production quality systems like Linux. Okay, so how does this class fit everything else? So at this point, I teach the following. So 5460 undergrad/graduate operating systems, x86 based class, essentially a first introduction to systems. It's pretty good. So if you go through that class, you already know stuff. You understand the words like page tables and stuff like that. You know, hopefully you have the whole x86 kernel, so you know what an operating system kernel might look like, but that's very basic. You stop there. And these two classes, and they can be taken out of order. The idea to have like the class which we are doing right now, 5965, it's concentrated on implementation, meaning build your own OS, and with the goal that you will be able to understand how other OS are built, like Linux or whatever this embedded systems OS, which OS which I mentioned, and you might get a career out of it. Occasionally people are asked to build anyone, and you will be getting it in your resume. It will allow you to get this position, essentially saying that I build one class, so I can build one for you as well. And the one which I taught last year, which some of you guys took, which was kind of a mix, maybe the idea in the future to make it more pure and essentially just like talk about the research directions in this field. So the idea is that if you take all three, you have the basics, you can build your own, and this research-oriented class will expose you to where the community is moving, so you can kind of guide and steer the direction and implement your own OS, right? So, any questions? So the hope is that you can essentially try to make money out of it when you graduate. Okay, our next question is, why are we pushing for Rust? So who can tell me, what is the reason to choose Rust over anything else? Security. So how does Rust improve security?
Avoid some common mistakes in C.
And how is it achieved? I agree with you, but how does Rust help?
It's type system.
Type system. So borrow checker is part of Rust type system, but Rust type system implements safety, right? So you have a safe language, and borrow checker is this funky trick which allows you to implement safety without garbage collection, because we have a bunch of safe languages. Java in the past, C#, Go, right? All of them are using garbage collection. So at a high level, okay, so for a while, I mean, people try to build the operating system in all those safe languages. It's totally possible, right? So you can like find a bunch of prototypes online. There were some production quality prototype. Microsoft tried to build something they built Singularity, and then they tried to build a production version, which was called Midori, right? Doesn't matter. The names don't matter, but those were building a dialect of C#, right? But safe language. Safety guards you against a lot of low-level mistakes, and we will talk about them later, but at a high level, like dereferencing a pointer which points to some random place in memory, right? But borrow checker also forces liveness of all the objects, right? So, okay, so what is Rust versus, I mean, first of all, do we understand safety? What is safety? One more time, I just wanted to stop for a sec. Before we started like assigning homework assignments about Rust, let's understand safety.
You don't want to be able to read memory.
I know, tell me. And again, like at a high level, my stuff doesn't work. But why? Because I'm teaching the first class in ages, right? That's why. Oh no, because I updated. Oh, okay, cool. That actually kind of works. So safety. Is there like a PL person in the room who can give us a definition of safety? PL programming languages. At high level, you're right. So what you're saying is that you're kind of saying that every time every time you have a pointer and it points to something, right? Some object on a heap or maybe on a stack, right? So in memory, right? You want to make sure that a couple of things are at a high level. You say, look, like what we want to do is that make sure that the pointer points to something what makes sense, right? The question is like, can we narrow this definition what it makes sense? So there are those things. So first is you want to ensure like, and I mean, there are maybe more rigorous definitions of safety. I'm not trying to be a very pedantic person, but pragmatically, you want to make sure that what you're pointing to is the type you expect. So meaning that type of the pointer matches the type of the object. In C, it's very easy to get it wrong, right? In C, any void pointer can be typecasted to any type, right? So some funky errors like tagged unions, which allow you to implement polymorphism, meaning that one interface can take different objects of different type, can very easily make a mistake. And it's like we did a study of vulnerabilities in the Linux kernel. Those are quite common, right? So you want to make sure that type matches, right? So that's called type safety. What else? Spatial. Spatial safety means that if there is an array of those objects A, right, you roughly speaking stay in bounds, right? So sure, that's easy to say, looking like when I access the object in memory, array in memory, I will check that the index is not out of bounds. So it's a little bit of an overhead, but otherwise works. And type typically can be checked at the level of the compiler, right? What else? Type and spatial. What next? Liveness. So what is this liveness? Or temporal? What is this temporal safety? And this is where Rust is different from other languages.
You only keep the object alive, and then it's
almost. I would almost agree is that I mean, let me just answer. Like, let me take a couple of answers, and I'll come back to you.
like you can't have.
Correct. So in a way, like both of you are correct, meaning that first of all, but those rules they kind of like get nuanced, and maybe I'm not going to be able to get all of them right. But roughly speaking, when you have a pointer to memory, you know that it's pointing to the live object, right? Meaning that it's allocated and was not deallocated, right? So it's alive, and that's live. You said that in Rust, in many safe languages, especially the ones which want garbage collector, you actually deallocate objects which are no longer used, right? Such guarantee doesn't exist in Rust specifically, but in Rust, it's safe to leak memory, which is kind of funky. You say, look, is it an attack if you just allocate a bunch of stuff which never gets deallocated? Like, it depends. But at a high level, yes, the idea is that if you have a pointer in memory, it points to an object, right? And ideally, you would like to have a property where when you say the object was allocated, got deallocated, and was allocated again, in C, it's kind of like works because it might not like trigger an exception, right? Because you're still accessing an object, but it's a different object. So semantically, in most cases, semantically, it's wrong because maybe it has a field which is not 0 but 1, and you will have some kind of a semantic error, but it's maybe safe in some languages. So in most safe languages, it's not allowed, right? So I don't remember a safe language which allow you to deallocate and reallocate memory, have a valid pointer.
I think it has good liveness analysis because it's type systems based on affine logic, which means an object can only be consumed once or at most once. So when it's consumed, you're already good to go. It's destroyed. But if it's not, they statically like figure that out and then they add drops or
No, that's correct. In Rust, but that's all correct. We will get to it, and I'm not an expert either, but at a high level, what you're saying that this affine logic, or we call them linear logic, affine is probably more flexible. Means that object the way Rust solves this problem, and I will explain in a second, is that it allows each object to have one pointer pointing. If you assign from one pointer to another, you cannot use the first point, but in the end, you can, when the last pointer goes out of scope, meaning no longer use it, you can deallocate object. But in Rust, you still can leak memory. It's okay. But roughly speaking, and I mean, and you can start talking about what about race conditions? Is it safe to access the object from multiple threads? Is it safety property or not? That's where probably PL people should kick in. We can stick here and maybe talk about synchronization if we want, but roughly speaking, this is your safety, right? So you guarantee to access the object of the same type. You don't go out of bounds, and the object is alive, right? And that's a powerful property. Like you said, guys, it doesn't exist in C, it doesn't exist in C++. You can make a mistake, and I can teach a class on like what kind of funky mistakes you can make in a Linux kernel and how many of those. And some of them are completely, they will blow your mind. It's crazy that it's great that this like funky setup is possible and you can make a mistake here. But Rust and other safe languages solve you, guard you against making those mistakes. They don't always help because Rust is really two languages: safe subset of Rust and unsafe. Unsafe, in the unsafe subset, you can do whatever you want. It's like C. Assign any pointer to anything, then you might end up with a similar bug in a safe subset as well, just because you screwed up the safety guarantees. But again, just one more time, Rust. Historically, in languages like Java and C#, you have a pointer, allocate an object on a heap. You're free to like essentially assign this pointer to anywhere else. And at some point, something goes out of scope, and then maybe B goes out of scope. Because of the temporal safety, the language guarantees that this object is alive, right? Because otherwise the access of like any last pointer would be unsafe, right? But at some point you have to make a decision, okay, is it safe to deallocate this object? And what do these languages do? Java, C# to solve this problem? Correct, yeah. And I'm not an expert on garbage collectors, but the simpler ones are really simple, complicated ones are insane. But it's garbage collection. So essentially you scan the entire heap, not just heap, but stacks and everything, where I don't even know what the entry points to the garbage collectors are. And you say, look, is anything pointing to this object on heap? And if the answer is no, then you say it's safe to deallocate, right? But this, of course, this scan of the entire heap and everything else, like stacks and all, anywhere else you can save those pointers, is time consuming, right? And safety was great. For many years, people were trying to use build safe kernels because, like, remember my slide with 700 vulnerabilities? My expectation is that 70% of those vulnerabilities will go away because they are safety related. I will show you a slide in a second. But this garbage collection scam is expensive as hell. And historically, that was kind of a showstopper. That's why we have kernels. Linus Torvalds will never allow him to run something like C# in a kernel, right? Because he says, no, right? How does Rust solve this? Rust makes this funky design choice. They say, look, and this design choice was like known for kind of forever, for a long time in the PL community, but typically those languages, they were so impractical that you cannot code anything useful. The design choice is the following. So this linearity. If you allocate an object on a heap, you allow only one single pointer into this object. If you pass this pointer assigned from A to B, then if you try to access A again, or access vector through A again, then the compiler just rejects the code saying that you're breaking the rules. But this gives you a guarantee that the moment B goes out of scope, you know that it's the last pointer, just because of the restrictions, right? And so at this point, as Axel mentioned, you would just say, look, I will instrument the code with a drop method, kind of like a manual deallocation in C, and you're lucky, you just deallocate this object. And like both type and spatial safety are kind of similar between Java, C# and Rust, right? They're like compiler type inserted checks on the index bounds or type analysis and stuff like that. But the temporal safety is different between Rust and all these other languages. The major breakthrough is that you can do it without garbage collection, but with the additional pain of dealing with those single linearity rules, right? And this is implemented with the Borel checker, and that's pain in the butt. And but people learn how to use it. It depends on what kind of code you're writing and how safe you're trying to be. But it's a little annoying, guys. But that's the main breakthrough. Just to convince you that it actually makes sense. So there was this team which, let's say 5 years ago, 2019, they said, okay, we're going to build a device driver, I think in 10 possible languages, ranging from something as slow as Python to the fastest one, C. So C is a flat line at the very top. It's our golden standard, optimizes health, right? Here we have Python, which is 0, essentially 0, 0, 0, 0. And this is it's a user level device driver, part of the data plane development kit, which runs a user level device driver in Linux. And we are using, I think in this study, they use both 10 Gbps and 40 Gbps Intel interfaces, this X520 network interfaces. So those are reasonably fast, especially 5 years or 6 years ago. And because C, and this is the packet batch size. So realistically, one packet is unrealistic because you never receive one packet. 2, 4, kind of. So like 8 and 16 are typical realistic batch sizes. 256, you're really pushing it. You have to be like some kind of network intrusion detection company which just receives packets. And obviously, those languages which used to be considered to be like fast, like the blue line is, sorry, let's get to blue line later. Something like Go, C# and Go. So Go is this green line, C# is this orange line. So towards the end of this packet size, they kind of approach the max performance, which C gives you, right? But on realistic packet sizes, 8 and 16, even the fastest languages like C#, they're like 42, 36% slower. That's an overhead of safety. And actually, the funky part is that in this specific study, I don't think that even garbage collector is, which is an interesting thing on its own. I think they reuse packets, so there is no garbage collector. We should read again this paper. But okay, so that kind of sucks, right? So like, how can you lose 42% performance and say that it's a meaningful system? So it's probably not. And Rust kind of was this first language which was able to approach this whole overhead of like 10%. And it's also arguable because you can optimize Rust a little bit more, then probably will get close to C. So essentially, that's essentially the reason I'm kind of pushing for Rust. So Rust allows you to build low-level systems code which stays fast. And as I said, in this space, everything is about performance, right? I mean, there's some security guarantees as well, but really people, if you lose 5% of performance, it translates into millions of dollars, not billions. People want to stay fast. So that's why those safe languages never caught up. But and Rust was the first one which essentially is an answer, right? And as of today, probably let me give you like a state of the art. Each time still sometimes. State of the art is following. So production companies like Microsoft started rewriting parts of their low-level systems tool chain in Rust. Like, as of a couple of years ago, you could just get a job saying, I know Rust and systems, and you get a job. It's not as easy anymore. Amazon got to the point that they even want to take control over the Rust ecosystem. They're so powerful and use Rust in production so heavily that they started, I'm not an expert on those like kind of political games, but people are complaining in the community that they exert too much pressure on the community when they want a specific feature or anything, right? Okay, sure. So Microsoft, Amazon, Linux kernel allows development of device drivers in Rust as of last year, I think. So they developed this framework, which is called Rust for Linux, which allows you, after many years, like Linus Torvalds rejecting C++ from the kernel and punching everyone in the face, as you even mentioned it. Now it's utterly allowed to people to do Rust. The community is split, actually. People say, look, guys, it's almost impossible to maintain because like C moves forward a little bit, like an interface breaks and everything becomes unsafe and all your safety goes to hell. But maybe there is still a solution. But the idea was that they said, look, we have 17 million lines of code. They're like hack exploitable, maybe rewrite, or at least start writing new device drivers in Rust and get safely, right? And so it's kind of there. So Rust is useful. So when you say, yes, I'm going to learn Rust in this class and become an expert in Rust, if you're staying in the systems field, it makes sense. If you're doing something else, that it probably doesn't make that much sense. Rust is not ideal. It's a language with all sorts of like weird, like not production ready libraries and whatnot and weird type system rules. And you cannot say that maybe it's the best for task X, but for systems programming, just make sure that you understand the benefits. Just one step in practice, this performance game is a little bit trickier. So this is from our own work, which I mentioned before, Bradley, published with the I-2020. And here we compare performance of two hash tables, or like three hash tables. One written in C, and that provides us the reference performance number at 1. And then we normalize performance. And we have two, like, blue lines are idiomatic Rust. I'm following the Rust book as a good student. And it's kind of a little soft for me here, especially like at 20. I think that was 20 size, power of 2. It kind of like drops to some ridiculous number, which cannot be published in the paper, right? So that's not ideal. And in general, kind of lags behind. If I say, guys, I got sick of Rust, idiomatic Rust, I'm still will be coding. Everything is safe Rust, not non-safe Rust. But I say I'm going to use Rust as and I code the same hash table, like dropping option types, these are and some other things. My Rust actually, depending on if I'm lucky with the LLVM compiler, sometimes is even faster than. Because being faster means that you disassemble the code. And by the way, Rust allows you to get a human readable assembly. That's kind of a huge benefit for systems building, because if you build your systems in Java, you disassemble it in Java bytecode, so you need to know the bytecode and whatnot. In Rust, you disassemble, it's really readable disassembly. But like the compilers sometimes see them, it's almost the same assembly, but maybe the loop is unrolled or like managed, the loop condition is managed, not at the beginning of the loop, but at the end. And somehow on this weird hardware, it is faster. So there is no inherent reason for why it's faster, but at least it gets to the same performance.
There is a reason that sometimes Rust is faster than C, and it's because Rust has stricter aliasing rules for pointers. And so LLVM and GCC, if they can't prove that two pointers don't alias, then they have to be more conservative on certain optimizations.
That's actually a good point. And I was actually asked once this, and I wasn't able to come up with the answer, so good that you can. But that's right. And if you know, send us a link, we'll look at it in what cases it actually happens. In my case, the code was so simple. There are no pointers, nothing with numbers, hash table. You disassemble, it's like fits on one screen, like loop of this hash table. It's almost the same between the two compilers, and somehow just the choice of optimizations of the specific compiler gets you ahead. But you're right that in some cases, the proof that pointers don't alias and stuff like that will allow you to like reduce some, eliminate certain checks, and I don't really know which ones, but you're right.
It also could just be that the REST compiler has a few optimizations before it heads over to LLVM.
Can be,
But
yeah. And I think actually here, which is also wasn't super fair, it could be that we compare GCC versus LLVM, because I asked for the LLVM, why we didn't pick LLVM? I don't remember, maybe like maybe just proof or something, I don't know. But roughly speaking, my point is that that in many cases, if you're very, very careful with your ROS and you want to give out certain high-level language features which automate your development, but you really go after the level of performance, most likely this blue line can be shifted towards the back, this careful code. And it's still safe, so everything is safe code here. So that's great, and we say, look, okay, we're buying this vision. Someone said Rust gives security, right? So Rust gives you security, better security through safety. There were studies, and I will show you one like graph from Microsoft researchers from Microsoft. We did similar studies about the Linux kernel, kind of came to the same conclusion. Roughly 70% of vulnerabilities will disappear. So here on this plot, that's from Microsoft presentation. The break-in by classes of this blue area is stack corruption, stack overflow, and essentially with the compiler tricks, without even C or input, without Rust, you can implement enough logic to kind of get very small numbers. Those buffer overflows are addressable. Heap corruption kind of sometimes goes out, but still stays like the size function. Heap corruption meaning this out of bounds access kind of array of I assume. Use after free is this liveness violation. Essentially, someone delegates an object and then someone accesses it later. And it's pretty common error because, especially in a concurrent environment, imagine either two processes are running, one delegates an object, but the second one still has a pointer, and there was no signal to say don't use it anymore, don't delegate, right? So use after free is pretty common, states there. Kind of confusion, which I mentioned, this type saving, right? The object type A stays type A, still some number stays there despite the fact that they tried to address it over the years. Uninitialized, use of uninitialized code in unsafe languages like C is pretty common as well. Deep out of bound read, not sure what's the difference between heap corruption and deep out of bound read, but happens as well. And there is this blue chunk, which is other, right? And the expectation here is that those roughly 70% of them are safety related. And roughly speaking, not each of them, but many will be addressed by Rust. Rust, roughly speaking, will not allow you to write the code which compiles, right? It's not exactly true. Like, who can correct me here?
What they have lazy engineers, if they don't get the bar checker, may just hop into unsafe Rust and still write.
That's correct. And sometimes actually it's very hard to get. Not everything is programmable in safe Rust. So especially like different interfaces, like with unsafe libraries, with hardware. So unsafe boundary can be a source of vulnerabilities, right? But even in the safe code, like, will they disappear completely? Or what will happen to them?
I mean, this is kind of pedantic, but like there are a couple of unsound bugs in the type system. But
Yes,
it's
it's
like
related.
very, it is very rarely. So it's really
I'm looking for something. My simple case is like some of these safety guarantees are enforced at one. And so those bugs will kind of what is it called? Lower from like full exploit to denial of service. Essentially, it will be an exception. And you say, well, oh, suddenly access out of bounds, but I didn't handle it anyway. So it's not an exploit, but you crash this. Like, and if it's in the kernel, it's kind of, device driver is no longer working, so your kernel probably should shut down. So some of those vulnerabilities will be turned into denial of service. Again, we did a study with Jerry and other people, and you're right, there are some funky cases which are often, I don't want to go into this right now, but So 70% of those disappear. However, 30 stays. So what are these 30? What do you think these are?
Logic bugs?
Logic bugs, right? So like some kind of semantic bugs. You say, look, this has to be sorted. You can become, it's not sorted, or maybe not all the elements will return back from this sort, right? They just disappear or something, because I wrote it. Or ChatGPT wrote it. And but all sorts of things like lists are acyclic, so they don't have a loop or something along those lines. So surprisingly, still 30% of those are there, and they exist in any safe language as well, not just specific to Rust. But still, it's a good step forward, right? So you're saying, okay, 70% low level, the most kind of like dangerous bugs which immediately give you control over the system, because logical bugs are harder to exploit. Imagine you return 0 versus 1. Well, maybe something bad happens and you immediately reboot as root, but maybe nothing happens. You just say, look, I will not set a packet. Well, TCP is not reliable anyway, right? Okay, so we get it. So safety of Rust is a good thing. So our team, we were among the first ones who said, okay, we're going to use Rust as actually, there's this funky property, which I don't know if I have on the screen. So Rust, like kind of the main argument which the industry gets is the safety argument, right? But they usually stop there. There is a couple of non-safety, or if you like, beyond safety arguments. The arguments are about different properties which Rust provides you with your software, which allow you to make it maybe more secure or something else. In our case, more secure. We say that the safety of the language allows you to kind of like draw isolation boundaries between individual parts of the kernel, saying that each device driver runs in isolation. There is a bug there, it will crash, but the rest of the system will go on. And maybe you can even restart it. And, you know, in a C kernel, it's almost impossible to do. In Rust, it's always also almost impossible to do, but at least you have a hope. And so we use this relative physics, the operating system kernel, which exercises this argument kind of we draw this isolation boundaries around everything what we can figure out. NVMe device driver runs in isolation. HDD runs in isolation. File system runs in isolation. We deal with like different file system sessions in isolation, not in our system. Different TCP protocols, stuff like that. In a regular kernel, this is impossible because crossing the isolation boundaries is very expensive, and you cannot do this fine-grained level of isolation. By the way, if I ask you from a daily life, what is the example of similar isolation argument in the software which we run every day? Which
Browsers.
web browsers, correct? Because they are so critical for us that like Chrome was the first one to say individual apps run as individual processes. They don't communicate very frequently. That's why, you know, performance hit is minimal. Mozilla Foundation, which stood behind Rust, said that we're going to rewrite the web browser. I forgot the version which they called Firefox, a bit so, right? But the Rust engine is, I forgot the name of the research project. Doesn't matter, but essentially the same idea, so kind of like isolate, so it's harder to pound to own this system, right? So this is kind of an argument beyond safety. But here, let me get to you like 10 more, 11 minutes. The last, arguably at this point, this was very hot, this is 5 years ago. My best research, but 5 years ago. I got a job offer from the University of Utah. I talked about this. I don't know if now it works, but now I have a different argument. And this argument kind of is a future-looking argument, which you have to hopefully exercise in your life. So Rust, surprisingly, provides a gateway to practical formal verification. It's a little unusual, right? Because what is formal verification? You say, look, I will write a formal specification of what my software is supposed to do. Let's say it's a list, and you expect that you pass an array of elements, you get an array of elements, specification says that they are all in, let's say, ascending order. But second, it's the same elements which you pass, because if you pass zeros back, it just doesn't count because it's not very useful, returns zero. And formal verification allows you to make a proof, formal proof that the code which implements the sort function actually conforms to this specification. It's mathematical argument. If you do classes from Ganesh or maybe from Pavel, one of who teaches band, right? You say, look, I get it. It's a useful idea, but it's a mathematical proof. If you get to it very carefully, you can write those proofs about your software, but it's hard. It's labor intensive, and as the software gets larger, it becomes impractical, right? The first proof verify hand, right? But imagine you write a proof about x with 6, if you remember x with 6 code. Well, it's hard. It's like 10,000 lines of code, but you know how long it will take you to write a proof about everything. It turns out the first formally verified microkernel, this is CL4, which I mentioned, it took them many years. So roughly five people or 4 people for 5 years, right? It's a lot of time. And with Rust, it suddenly becomes a lot more tractable, or at least we claim as a team. So roughly speaking, what it means, there is this tool chain, which is Verus, which is a SMP-based verifier for Rust, which allows you to write Rust code like a page table, and it can allow you to mix something what is called proof variables or ghost variable. And this ghost variable is a map from virtual addresses to roughly speaking physical addresses, but it's physical addresses without permissions, right? So it's kind of like a page table. And you say, look, I know that this page table with pointing to the root of the page table with CR3 is always abstracted as this map. And you formally specify how you abstract it. And then you say like then you can talk about things. I'll add a new virtual address, and you manipulate the page tables, maybe allocate intermediate levels, nodes in the page table, but you still have a proof that whatever your code does, there will be preserved a specific virtual to physical mapping. And you can write those things in Rust. So this is from Atmosphere, this new operating system which we're building. It's a specification function for the mmap system call, which roughly speaking says that if you have an old version of the kernel and a new version of the kernel, and there's a thread ID which invokes the system call and asks allocation of memory for these virtual addresses with specific permission bits, it will return a specific value, and then you specify, you write what mathematically, what is supposed to happen. So I will give you a couple of examples. So you can write something that you do mmap system call, but for example, threads are not changed. You don't change the threads. You didn't delete the thread, you didn't actually like this is the code. Okay, threads aren't changed. It's a little unusual because you think, oh, like, oh, but what if you like really your code like overwrite the thread data structure or something like that? Like higher level properties like virtual addresses outside of this virtual range, which I'm allocating, are not changed. That's a useful property. You know that your mmap system code that will not change anything. Newly allocated pages are actually coming from a memory allocator and stuff like that. Otherwise, you know, maybe you just reallocated, like you made a mistake and you remapped one page into another location, right? But really it's something funky and you say, look, guys, and at a high level, and then you like actual implementation of a function, and the theorem prover proves that, you know, you get this. It requires that you had like the kernel is well formed all over the place, like all the linked lists are correct, stuff like that, and ensure that whatever the mmap system call, the actual Rust code which you write, will adhere to this specification. And you can build proofs like what you want to say, functional correctness, meaning that system calls do what they supposed to. You can reason about cross-cutting global invariants, meaning that all the lists are well formed. There are no loops. There are objects on one list, but not on two, for example. Rust type system will not like, it may guard against certain bugs, but that's called like semantic. So those 30% of semantic bugs are actually addressed by this proof. And this safety and leak freedom, the 70% are also addressed. And actually Rust doesn't provide leak freedom. You can reason about leak freedom as well. And higher level properties like process A cannot like exhaust memory of process 2. And I mentioned that it becomes practical. That's a commit log for our Atmosphere microkernel. We built 3 versions like over the course of roughly 2 years. like the first one, basically a toy prototype. We were learning how to use verse. Then we dumped it, started clean slate, introduced like specific design decisions, and then finally build a third version with better properties. And roughly, it took too many years to build a fully verified microkernel. And an additional interesting detail that maybe only 1.5 years were spent on verification. The rest was spent on like regular, let's build unverified device drivers in Rust, but who knows what they're doing and stuff like that. So that's kind of more powerful than like anything what I discussed before, like safety and those isolation arguments. This is like a formal argument, and Rust like is a language which allows you to essentially cut significantly the cost of verification effort. And just to give you an example, there's a couple of metrics here. It's verification, like we verify the microkernel on 2 machines. The blue one is a powerful laptop. The red one is an older server in the Emulab data center. And on this fast one, verification of the longest function takes 7 seconds, which is kind of remarkable because it's faster to run the theorem prover than to reboot and test your kernel, right? In practice, the anecdote is that we found only 2 bugs in this microkernel. One was a bug in specification. We didn't write correctly what we expect the kernel to do. Second, whereas our version doesn't reason about loops, and there was an infinite loop, which we did catch. But essentially, roughly speaking, what's important here is that if for each line of code, you have to write roughly 3.2 lines of proofs and specifications of proofs. And it used to be that a CO4, which I mentioned, the ratio was roughly 1 to 20. So that's why a significant reduction in proof effort. So this is where the future is. Essentially, the belief is that all the companies will gradually switch to verifying their sensitive or mission critical code. Our buddies from Amazon are aggressively hiring. We'll hire all of you if you get to Verus at some point. That's essentially, that's fun. Okay, so let me then leave you with this slide, and now let's quickly take questions if we have any. I used to write something like, we're going to rewrite this kernel in Rust, but no, these days I believe that we're going to verify it. And like obvious kind of, okay, one important observation here is that the future of code might look like this, which may not be true, but let's think about it. You say AI can generate a bunch of code. You never know if it's correct or not, right? Because maybe it just bugs out or whatever, right? If you didn't get the constraint, right? If you use a formal specification like the one which I put on the whiteboard on the slides, where you specifically say, I expect the code to do this, this, and this. That's my specification. Then you can use AI to automate the proofs and maybe even synthesize the code in between, right? But AI cannot bug at this point. It can, but the prover says, okay, you bug, you have to like generate other, like refine your proof, right? But the moment the proof is correct, you have a formal mathematical proof of correctness. And that's probably how you will write code in the future. So you just write specifications, and then AI and theorem provers will fill in the gap. And this is already there. So people are trying to publish like their submissions, something like AI generated various proofs and stuff like that. Arguably, not everything AI can generate, but that's why we humans still like write those funky, like the success of Atmosphere and this remarkable speed is in several non-trivial or and they are kind of trivial but counterintuitive design choices which allow us to reduce the speed of like essentially complexity of the proof. So AI cannot really do this, it just doesn't have an idea how to do it. But nevertheless, that's where we are. Okay, so let me stop here, and I'm right exactly on time, which is rare, but I'll come back and let's most likely I will try to assign something like let's start digging through the Rust book, so we will already just at least start looking at Rust code. And I'm not that good at Rust, so you guys will be disappointed, but still, let's start. So thank you. I'll see you then Wednesday.